So we've got an awful lot going on here in this idea of trying to introduce slope to pretty much any kind of function that we can imagine and draw. We've started off with the idea that we can at least kind of figure out what the sign of the slope should be by just simply kind of walking along the graph. We can determine whether we're plus, we're walking uphill, or minus, we're walking downhill, or if we're potentially zero, if we're walking horizontally. We could also consider trying to walk straight up and down vertically, and that would imply that we have no slope, or that slope is undefined. So we have a variety of different things that we can read kind of off the graph, but we can't get numbers. So then we've introduced this idea of the slope of a tangent line. So we take the limit as delta x approaches 0 of f of c plus delta x minus f of c, all divided by delta x. That gives us the slope of a tangent line, and we define the slope of the tangent line at some point c comma f of c to be the slope of the function at that point. We're assuming that the limit exists when we do that. If the limit doesn't exist, then there is no slope of a tangent line at that point. And that does happen in some places. The difficulty with the definition as we've given it to you so far is that if you want to find slopes at lots of different places on a graph, you have to go through this limiting process for each value of c. So let's say that you have 12 different values of c. That's 12 different runs through this limiting process. And this limiting process isn't necessarily a short and quick activity. So what we would like is a way to do this a little bit faster. All right? I'm going to show you one way here that still deals with a definition. When we get into later lessons, we'll speed things up even more and become even more efficient with finding slopes of tangent lines or finding derivatives. All right? But here's what we're going to say. We're going to say that we start with a function f of x. And we're going to define something called its derivative, which we can write as f prime of x. And we'll talk more about notation in some later lessons, but for now we'll just use f prime of x. It's a common notation. It's one of many notations, but it's the one we'll start with. We're going to say that that is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. So notice that what I'm doing is I'm replacing the c's. C's were specific numbers. I wanted to find the slope when x is 2. I want to find the slope when x is negative 5. And we're replacing c with the letter x. This leads us to a function. All right, this is something known as a derivative function. And it's something that we can evaluate. Notice the function notation at the beginning. F prime of x, that's how we read that, f prime of x. We can replace whatever we have in our result from going through the limiting process. We can replace the x with a number. And we can just go through and essentially plug and chug. It's just some quick substitutions. So if we have 12 different values, 12 different places or x values where we want to try to find the slope of the graph of a function, once we have that derivative function, we can just plug things in. And we'll be done very quickly. So this is the form of the rule that we're going to use more regularly. And as we'll find out shortly in some later sections, there will be some shortcuts to using this rule, but we're not going to find out about those shortcuts until we've actually learned how to use this rule and hopefully get a little bit better understanding of what this rule is and how it works.